I am Shivam Handa. I'm here to tell you about my work on inductive program synthesis over noisy data. This is joint research with my advisor, Martin Rinard. I will start by reviewing inductive program synthesis. A synthesis algorithm in this setting, given input-output examples and a DSL, finds a program from that DSL which satisfies all input-output examples. This means all input-output examples need to be correct, because if you get one of them wrong, either of these two things can happen. Either the program synthesis technique will not return you any program at all, or it will return you the wrong program. But of course, the real world is not like this at all. In the real world, there is all kinds of noise in your data. Now, if you want to use program synthesis in the real world, we have to deal with noisy data. The first question is, what do we even want our program synthesis algorithm to return? Clearly, we do not want a program which satisfies all input-output examples, because some of them may have noise. What we want instead is to find a program which best fits the given dataset. We formalize this notion of best fit using the concepts of a loss function, a complexity measure, and an objective function which combines the score given by the loss function and the complexity measure. A program is a best fit over the given noisy dataset if it minimizes this objective function. Formally, the objective function combines two scores. First one is the loss, which measures how incorrect a program is with respect to the given dataset. And second one is the complexity measure, which measures the complexity of a given program. The complexity is independent of the dataset. The complexity metric is similar to a regularizer in machine learning. It biases the synthesis algorithm towards synthesizing simple programs. Now, the question is, what kinds of loss functions can we use? The framework doesn't have any special restrictions on the type of loss functions we can use, but we'll go through some example loss functions. For example, this is a 0-1 loss function. It just counts the number of examples a program is incorrect on. If you wish to find a program which satisfies the maximum number of input-output examples, we may want to use this loss function. The next one is the Demirel-Levenshtein loss function. This loss function is specifically constructed for programs which work on strings. It uses the Demirel-Levenshtein distance metric to calculate the edit distance between programs' output and the corrupted output. The Demirel-Levenshtein distance is widely used in string processing because it catches a large number of typing errors human makes. The Demirel-Levenshtein distance is the minimum number of deletions, insertions, substitutions, or transpositions required to match two strings. For example, in the first case, to match Ducati to Ucati, we need one deletion. To match Honda to Conda, we need one substitution. To match Ducati to Udacati, we need one transposition. To match Ducati to Ducat2, we need one deletion and one substitution. We can be even more specific in our choice of a loss function. For example, this is the one delete loss function. Now let's say we have a noise source which in worst case can only delete one character from your output string. We can then use this precise loss function to match the noise source. This loss function returns 0 if the string match, returns 1 if the strings only differ in one character which has been deleted, and infinity otherwise. Another specialized loss function is the n substitution loss function. It counts the number of substitutions required to match these two strings. Now let's go over some examples for the complexity measure. Our framework allows for a large class of complexity measures. A good complexity measure, for example, is the size of a program. We wish to find smaller programs rather than larger programs that overfit the data. By using the size of a program as a complexity measure, our algorithm will be biased towards finding smaller programs. Now let's have a look at some example objective functions. This is the lexicographic objective function. It first finds the set of programs which minimizes the loss function, and then within that set finds the program which minimizes the complexity. What it's doing is it's first minimizing loss and then minimizing complexity. There is another important objective function called the trade-off objective function. It allows us to trade off between loss and complexity. The idea here is we want to minimize both loss and complexity simultaneously. But we are willing to pay some extra loss in order to get a more simpler program. Next, we are going to present some experimental results to show how our technique works in practice and how the choice of loss function affects the synthesized program. For these experiments, we use the SyGuS 2018 programming by example benchmarks. These programs manipulate string. There are 108 benchmarks, each containing 4 to 400 input-output examples, and some of these benchmarks have repetitions. For each benchmark, we introduce noise into the given examples and then compare the program synthesized in the noisy case versus the program synthesized in the noise-free case. Note that in general, the correct program is hidden, but since we are introducing noise in our experiments ourselves, we can compare these synthesized programs. The first noise source we experiment with deletes a single character in the output string. For example, given input Ducati 100, the correct program returns the output Ducati, but our noise source corrupts the output to Ucati by deleting the D. This noise simulates a common human error of skipping characters while typing. The goal of this experiment is to find the minimum number of correct input-output examples, different loss functions required to synthesize the correct program. Here, we present the results of our experiments on a subset of the given benchmarks. As you can see, these benchmarks contain relatively small number of input-output examples between 4 and 7. Now, let's have a look at the results for the 0-1 loss function. The 0-1 loss function counts the number of input-output examples the program is correct on. For this loss function, any kind of corruption is the same. Note that it needs between 1 to 3 correct input-output examples to synthesize the correct program. A question could be, why doesn't it need at least half of them to be correct? This is because of the strong effect the DSL has on the search space. There may exist no program which satisfies half of these examples even after corruption. Now let's see how Demirel-Leveshtein performs. This loss function closely tailors the characteristics of this domain. As we can see, in some cases, it requires 0 correct input-output examples. This is because Demirel-Leveshtein can even capture information present in the corrupted examples. For example, let us say the output of my program is Ducati, but the corrupted output given to this algorithm is Ducat. Since Ducati is closer to Ducat than some random string, 5 of the characters in these strings match, Demirel-Leveshtein allows the algorithm to extract such information, and therefore, even in this case where we have no correct input-output examples, the algorithm returns the correct program. Now let's have a look at one delete. This is a fantastic loss function in this setting as it matches exactly the noise source. Remember, the noise source in worst case will only delete one random character in the output string. In this case, you will get the correct program even if every input-output example is corrupted. This illustrates how the knowledge of the noise process can help us craft loss functions and synthesize correct programs even in the case of substantial noise. What happens when the noise source and the loss function do not match? Take the case of n substitution loss function. The n substitution loss function assumes that the noise source only introduces noise using substitution. Therefore, it assumes that the length of the output string and the corrupted output string will match. If it doesn't matches, then it returns infinity. Therefore, it requires all input-output examples to be correct to handle this kind of noise. So the takeaway from this experiment is that our technique combines the DSL structure, which provides a very strong form of regularization, the loss function, which exploits the information preserved in the noisy data and allows us to synthesize correct programs even in the case when all input-output examples are corrupted. Our next experiment involves a substitution-based noise source. This noise source simulates a human user which mistypes a digit when typing the correct output. We run this experiment on the phone series of benchmarks. These benchmarks contain 400 input-output examples with repetition. The noise process takes a random digit and replaces it with another random digit. Note that because of repetitions, this dataset may contain examples which map the same input to different outputs. For noisy data, our technique returns the correct program in 7 cases out of 11. In the other 4 cases, our technique times out. Note that the technique times out in these 4 cases even if noise-free data is provided. The interesting fact about our technique in this case is that it never synthesizes the incorrect program. Now that we have shown that we can handle noisy data, this framework allows us to solve a large class of interesting synthesis problems. For example, we can do complexity versus accuracy trade-off. Here we are trying to trade off between, the loss function and the complexity. We are willing to pay some extra loss for a much more simpler program. We can also do Bayesian program synthesis, where we find the program which maximizes the log likelihood of a program by splitting it into probability of data given the program and the probability of program itself. We can find the best program with a given accuracy. For example, in this case, we are finding the least complex program which has at max B loss on the given dataset. We can even combine synthesis problems in our technique. For example, in this case, we want to find a program which best fits the given dataset D but has a bounded loss on a subset of the dataset. One interesting problem we can solve is the approximate program synthesis problem. And that is where we have a restricted search space, but the data given to this algorithm is noise-free. This setting may be helpful to all synthesis algorithms as the size of the search space is what makes or breaks synthesis techniques. Normally, for existing program synthesis techniques, you are trying to find the perfect program which does not exist within the restricted search space, and the entire search space may be too large for your technique to handle. The idea here is to find the closest program to the correct program within the restricted search space. The closest program may be more helpful than having no program at all. We can also use our technique to clean data. Given inputs and noisy outputs, we synthesize a program. If the program is right, given these inputs, the programs will give you the correct outputs for these inputs and not the noisy outputs. Therefore, this serves as a great way to clean noisy data. Next, we provide a higher level view of our synthesis algorithm. Our synthesis algorithm is based on a variant of finite tree automata, which we call a state-weighted finite tree automata. A finite tree automaton takes a tree as an input and returns a yes or a no answer. That is, yes if the finite tree automaton accepts the tree and no if it rejects it. Similarly, a state-weighted finite tree automaton takes an arbitrary tree as an input but returns a real number as its output. This is achieved by attaching a weight to the accepting state of the automaton. Given a non-noisy input-output example, we can construct a SFTA which, given an AST for a program, returns the program's loss on the given noisy input-output example. Two SFTAs can be combined to create a new SFTA, which returns the sum of the losses represented by the individual SFTAs. This is our synthesis algorithm. First, given a dataset D, we construct a SFTA on each input-output example and then combine these SFTAs to construct a SFTA representing the entire dataset. Given a program, this SFTA will return the loss of this program over the entire dataset. Then for each accepting state Q of the combined SFTA, we find the program which minimizes the complexity measure within the set of programs accepting by that accepting state. For each accepting state, the weight of the accepting state represents the loss of the program on the entire dataset. We find the accepting state and the program which minimizes the objective function by iterating over all accepting states. Our algorithm guarantees that the synthesized program minimizes the objective function. You can find the finer details of our technique within our paper. Our technique, at the end of the day, can effectively synthesize programs even in the presence of substantial noise. By using the structure of the given DSL, the information left intact within the noisy data and a good match between the loss function and the noise source. We are the first paper to formalize best fit based program synthesis over noisy data and provide a technique which allows us to synthesize program over noisy data with deterministic quantifiable guarantees. This framework can be used in a variety of different scenarios, including but not limited to approximate program synthesis and data cleaning. The long-term goal of this project is to replace machine learning models with synthesized programs. We believe that we can learn programs over data, and it provides us with a much more cleaner way to think about machine learning.